Hello there, and welcome to the Dreamology. If you are someone who finds peace in the mysteries of the night sky, someone who likes to unwind by letting your mind drift among the stars, planets, and the quiet, infinite beauty of space, then you have found the right place to rest. Tonight, we are going to leave the familiar gravity of our solar system behind. We are going to drift gently into the velvet darkness between the stars, traveling to places where other planets orbit distant suns, and where the laws of nature create wonders that seem almost like dreams. On this journey, we will visit worlds that rain metal, planets forged of ice and fire, and lonely giants drifting through the silence with no star to guide them. Some of what you will hear might sound impossible, like a fairy tale written in starlight, but every word of it is real. Everything we see tonight exists out there right now in the quiet dark. But for now, get comfortable. Let your body sink into the surface beneath you. Let your shoulders. There are planets out there with temperatures hotter than stars. We know stars for their incredible heat, glowing plasma furnaces burning at millions of degrees, radiating light into the void. But believe it or not, some planets come close to that fire. One such world, known as Kelt 9b, reaches temperatures over 7,000 degrees Fahrenheit, a heat so intense it is hotter than many red dwarf stars glowing in the galaxy. Imagine a massive gas giant, orbiting so close to its massive blue star that it touches the very edge of the inferno. It moves with incredible speed, completing a full orbit an entire year, in just over a single day. This planet is tidally locked, meaning it is held in a permanent embrace, with one side facing the star forever, absorbing a relentless barrage of radiation, while the other faces the eternal dark. The heat is so overwhelming that its atmosphere is being torn apart, streaming out into space like a comet's tail, a long ribbon of gas glowing in the starlight. It is so hot that some worlds might be made almost entirely of diamond. Sounds like science fiction, a fantasy of treasure in the stars, but under the right conditions, it could be real. Some exoplanets, especially those formed from clouds rich in carbon, might develop in ways that produce planets composed largely of diamond. If a planet forms around a star with more carbon than oxygen, the ingredients available during its birth can lead to vast carbon-rich structures. One candidate for such a world is 55 Cancri E, a super-Earth twice the size of our own, which may contain an enormous amount of carbon under intense pressure. That pressure, deep within the planet's interior, crushing down with the weight of a world, could create vast regions of crystalline diamond. It wouldn't glitter or sparkle the way we imagine jewelry in the sunlight. There would be no light there, just darkness, heat, and unimaginable density. Still, the idea is captivating to hold in your mind as you drift off. A planet forged from carbon. A world WHE. Some exoplanets orbit two suns like Tatooine from the stories we know. In science fiction, we have long imagined twin sunsets, two stars sinking beneath a distant horizon, painting the sky in double colors. But now we know those strange skies might actually exist. Some exoplanets don't orbit a single star like Earth does. They orbit two. These are called circumbinary planets, and they move in beautiful, complex loops around pairs of suns that orbit each other. When the stars are close together, a planet can circle them both as if they were one, a wide, graceful path around a dual center. But if the stars are farther apart, the planet might orbit only one, tugged and tilted by the other's distant gravity. The result is a world with unusual light cycles, changing seasons, and double shadows stretching across the ground. These systems are rare and delicate, but they do exist. So the sky of some distant world may truly glow with two dawns breaking the night, and two dusks welcoming the sleep. A sky once imagined. There are planets where it rains molten glass. Some worlds are so alien that even their weather defies the imagination. Take HD 189733b, a gas giant larger than Jupiter, orbiting so close to its star that it completes a full orbit in just over 2 days. The planet's atmosphere is scorching, with temperatures hovering around 1,700 degrees Fahrenheit. Winds whip around it at thousands of miles per hour, faster than sound, faster than thought. And suspended in its blue, hazy skies are tiny particles of silicate, the building blocks of glass. When conditions are right, these particles condense and fall as rain. Not water, not ice, but molten glass swept sideways by the high-speed winds. From far away, this planet looks strangely Earth-like in color, a soft blue shimmer glowing near its sun. But up close, it is a storm furnace, beautiful, violent, and utterly uninhabitable. It is one of many exoplanets that remind us nature's imagination reaches far beyond our own. Others may be covered in oceans thousands of miles deep. Some exoplanets might be ocean worlds, planets almost entirely covered in water. Imagine a world with no continents, no islands, just endless global seas stretching in every direction. These aren't like Earth's oceans, which only reach a few miles deep. On these worlds, the water layer could be hundreds or even thousands of miles thick. At the surface, it might be calm, wind-blown, or stormy, reflecting the alien stars above. But deep beneath, the pressure would rise to incredible extremes, creating exotic forms of ice. Not the kind we know, but dense, high-pressure ice that forms under crushing weight, warm and solid. These planets may have rocky cores at their centers, hidden far beneath the water. Some may even have liquid layers warmed by internal heat. Could life exist in such oceans? We don't yet know. But ocean worlds may be more common than we thought. Gentle, glistening planets with no land in sight, quietly turning in the dark, far from NES. Some planets are tidally locked, where one side always faces the star. Not all planets spin freely like Earth does. Some are locked in place by gravity, meaning one side of the planet always faces its star, bathed in light, while the other remains in permanent darkness. The same thing happens with our moon. We only ever see one side. But imagine this on a planetary scale. One hemisphere scorched by unending daylight, an eternal noon that never fades, while the other is trapped in eternal night. Between them lies a twilight zone, a ring around the planet where the light is always low, and the temperature might be just right. Some scientists believe that in certain cases, life could survive in this thin band of balance, watching a sun that never sets and never rises. These planets may have fierce winds, strange cloud formations, and wild extremes in weather, but they are real, and they challenge our ideas of what makes a world habitable. Life, if it exists, might learn to thrive in the shadows or just on the E. Hot Jupiters skim so close to their stars, their atmospheres boil off. Imagine a planet like Jupiter, massive, gaseous, and immense. Now move it far closer to its star, so close that a single orbit takes only days. So close that temperatures rise beyond 2000 degrees. These are hot Jupiters, giant planets that skim just above their star's surface, so near that their upper atmospheres are literally being blown away into space. We have discovered many of these strange worlds, often among the first exoplanets we ever detected. Their sheer size and tight orbits make them easier to spot, but they are deeply mysterious. How did such massive planets get so close to their stars? Did they form there, or were they pushed inward over time by gravitational forces? Some trail glowing tails of gas like comets, painting a streak across the star. Others are slowly shrinking as their atmospheres evaporate. They are unstable, dramatic, and often short-lived. Brief flashes of planetary fire circling faraway suns. Some exoplanets are darker than charcoal. Not all planets reflect light the way Earth does. Some absorb nearly everything, becoming darker than paint, darker than ash, darker even than charcoal. One such world is Trace 2b, a gas giant orbiting a star about 700 light-years away. Its atmosphere reflects less than 1% of the light that hits it. Scientists aren't entirely sure why. It could be due to vaporized alkali metals or unknown chemical compounds in its upper layers. Whatever the cause, the result is extraordinary. A planet as dark as coal, glowing faintly with heat, nearly invisible in reflected starlight. Even its night side, already in darkness, is only slightly cooler than the day. If you could stand nearby and look toward it, you might see only the faintest silhouette against the fire of its star, a nearly perfect shadow orbiting in silence, absorbing the light of the universe. We found planets floating alone without a star. Most planets orbit stars, but not all. Some are wanderers, free-floating planets that drift through space alone, unbound by any sun. These are known as rogue planets, and we have found evidence of dozens, maybe hundreds across the galaxy. They might have formed normally, then were ejected from their home systems by gravitational disruptions. Or they may have formed in isolation like failed stars, never capturing enough mass to ignite. These worlds are dark, cold, and incredibly difficult to detect. But with powerful infrared telescopes, we can catch hints of their faint thermal glow. Some might still hold internal heat, keeping subsurface oceans warm for billions of years. Others could be completely frozen, drifting forever through the black. Planet without a sunrise, a world with no sky. And yet, even here, the quiet question persists. Could something live in such stillness? Some worlds may have ruby and sapphire clouds. When we think of clouds here on Earth, we imagine soft white water vapor, drifting lazily across a blue sky, ever shifting and gentle. But on some exoplanets, the skies may shimmer with the dust of gems. On scorching hot gas giants, where temperatures soar above 2000 degrees, minerals that would be solid rock on Earth can vaporize. They rise high into the atmosphere, cooling just enough to condense into clouds. But these are not clouds of rain. They are clouds made of corundum, the mineral form of rubies and sapphires. Imagine a world wrapped in heat and storms, lit by a blazing sun, with clouds of liquid gems glinting and swirling overhead. These mineral clouds may scatter light in strange and beautiful ways, tinting the skies deep red, purple, or a profound blue. On one such planet, HAT P7b, researchers have seen shifting patterns in the atmosphere that suggest high-altitude mineral clouds sweeping across the sky. It is hard to picture, yet the UNIV. There are super-Earths that could be more habitable than Earth itself. Some exoplanets fall into a category astronomers call super-Earths, rocky planets that are larger than our own world but smaller than the gas giants like Neptune. These worlds may have stronger gravity, thicker atmospheres, and perhaps even more stable climates than the one we know. And some of them may be even more hospitable to life than our own home. One such candidate is Kepler 442b, a rocky planet resting in the habitable zone of its star. It is not too hot and not too cold. It receives just the right amount of sunlight to potentially hold onto an atmosphere and liquid water. Some super-Earths could have deeper oceans, fewer tectonic disruptions, and greater surface stability, all conditions that might help life emerge and endure over billions of years. Of course, we don't know yet if any of these planets are truly habitable, but they remind us of something humbling as we drift through the dark. Earth may not be the perfect planet. We have seen planets that orbit in just a few hours. Most planets we know take months or years to complete a journey around their star. Earth takes 1 year. Even Mercury, the fastest planet in our solar system, takes 88 days to circle the Sun. But some exoplanets move much, much faster. We have found worlds that orbit their stars in a matter of hours. One of the fastest is Kepler 78b, a planet just slightly larger than Earth. Completes a full orbit, a full planetary year, every 8.5 hours. It is so close to its star that its surface is likely covered in molten rock, a world of lava and fire. Temperatures there reach several thousand degrees. These ultra-short period planets are often tidally locked, their days and nights frozen in place, while their stars loom huge in the sky. Gravity pulls at their structure, and some may be slowly tearing apart. These planets are extreme, fast, hot, and fleeting, but they exist, skimming the edges of their stars like sparks flying from a flame. Other planets take centuries to complete one orbit. While some exoplanets race around their stars in mere hours, others take their time, moving through the void on long, silent journeys that can last for centuries. One of the slowest moving planets we have found is Gu Piscium b, a gas giant that takes about 1,000 Earth years to complete a single orbit around its star. Its path is so distant that it is barely held by gravity. If it were any farther out, it might break free entirely and drift away into the dark. These long-period planets are incredibly hard to detect. We cannot wait 1,000 years to watch them complete a loop. Instead, we catch them in motion, noticing a curved path, a long arc, a hint of something vast moving in the deep. Some of these planets may have cold, dark surfaces, illuminated only faintly by starlight. Others may experience seasons that last lifetimes. On such worlds, change is measured not in years, but in generations. A slow and silent rhythm far beyond our own. We have discovered thousands of planets beyond our solar system. For most of human history, we only knew of one planetary system, our own. We knew the sun, the moon, and the wandering stars that moved through our sky. But everything changed in the 1990s when the first exoplanets were confirmed. Now, thanks to space telescopes like Kepler and TESS, we have found thousands of planets circling distant suns. Some are small, rocky, and Earth-like, while others are massive and strange. Some orbit tightly in just a few days, while others take centuries to complete a single trip. Each discovery reshapes what we thought was possible. And still, this is just the beginning. We believe there are hundreds of billions of planets in our galaxy alone. Think of that for a moment. More planets than stars. Worlds upon worlds quietly orbiting in the dark. We will never reach most of them, but we can listen for them, measure their shadows, and wonder what else might be waiting out there. We have detected planets using the shadows they cast during transits. The light from a star is usually steady, a constant beacon in the night. But sometimes just briefly it dims. Tiny dip, a momentary flicker. That dimming can mean a planet has passed in front of it. This is called the transit method, and it is one of the most powerful tools we have for finding exoplanets. When a planet crosses its star from our point of view, it casts a faint shadow. Not in the dramatic way we see with eclipses, but in subtle drops in brightness, often less than 1%. Space telescopes have used this delicate technique to find thousands of new worlds. From just those shadows, those tiny interruptions in the light, we can learn the planet's size, its orbit, and even find hints about its atmosphere. We are watching stars blink ever so slightly to learn about unseen worlds. The light of a distant sun interrupted by the quiet silhouette of a planet far away. Others were found by the gravitational wobble they induce. Even a planet's gravity can leave a fingerprint on the light. When a planet orbits a star, it doesn't just move around the star. Causes the star to move slightly too. This wobble is tiny, but it is real. As the star shifts back and forth, its light shifts with it, squeezed and stretched by motion. Astronomers can detect those changes using spectroscopy, breaking starlight into its components and looking for the subtle signatures of motion. This is called the radial velocity method, and it was how the first exoplanets were discovered. It works best for massive planets close to their stars, like the hot Jupiters we visited earlier, but it has also helped us find multi-planet systems and long-period orbits. We are not seeing the planets directly. We are watching their stars sway under that pull. like a dance too distant to see, but close enough to feel in the music of the light. Some exoplanets appear to have atmospheres escaping into space. A planet's atmosphere is never truly still. Winds blow, clouds drift, and particles escape. But in some extreme cases, the entire upper atmosphere may be drifting away, leaking into space like breath into the void. This is especially common in hot, close-in gas giants where intense radiation from the nearby star can heat the outer layers until they reach escape velocity. These planets can develop long, comet-like tails of escaping hydrogen and helium. We have seen this in several exoplanets where ultraviolet light reveals trails of gas streaming behind them. Some planets may lose significant mass this way over time. Others might be stripped down to their rocky cores. This process helps shape the evolution of planetary systems, showing how stars can sculpt, reshape, or even destroy their planets. It is a reminder that even worlds can change, erode, and fade, leaving only their gravity behind. We found planets in star systems with 3 or more suns. Not every star system is like ours, with a single sun sitting at the center. Some contain not 1, but 2 or 3, or even more stars orbiting together. And in a few of these complex systems, we have found planets. Imagine a world where the sky is never dark, where shadows stretch in different directions, where one sun rises while another sets. These planets must follow delicate, stable paths to survive the tangled pull of multiple stars. Some orbit closely around a pair of stars, while others orbit far beyond the entire cluster, tracing wide loops around a chaotic center. The lighting would be strange, the seasons unpredictable, and the sky full of motion. Yet these planets exist, and they remind us that planetary systems can form in ways we never expected, even in places where gravity is complicated. The night sky never settles there. Planets find a way. Some worlds orbit the collapsed remains of dead stars. Stars don't live forever. Some end their lives as white dwarfs, small, dense remnants of stars like our Sun. Others collapse into neutron stars or even black holes. And around some of these stellar corpses, we have found planets. These worlds orbit what remains after a star has died. Glowing embers or pulsing remnants of stellar fury. In some cases, they are survivors, somehow enduring the chaos of a supernova. In others, they may have formed from the debris left behind, rising from ashes into something new. The light from these stars is dim, cold, or distorted, but the planets remain, tracing silent paths through a kind of stellar graveyard. Some are blasted by radiation, others drift quietly, circling dead suns in eternal twilight. It is haunting and beautiful, a reminder that even after the end, something new and strange may begin again. One planet orbits its star backwards. Most planets in the universe follow a predictable path, orbiting in the same direction that their star spins. It is a cosmic rule of traffic, established when the system forms from a single, swirling disk of gas and dust. But nature does not always follow the rules we expect. We have found at least one exoplanet, known as WASP 17b, that orbits its star in the opposite direction. Instead of moving with the star's rotation, it pushes against it. This backwards orbit likely formed through chaos long ago, perhaps a near collision or a gravitational shove that flipped its path entirely. It is a massive, bloated world, orbiting close to its star every few days. The fact that it moves in reverse challenges our understanding of how planetary systems evolve. It proves that the universe is flexible, chaotic, and full of surprises. Some planets follow the flow, while others push against it, moving through the cosmos with a quiet, stubborn defiance. We have seen signs of clouds on planets light years away. It may seem impossible to see weather across such vast distances, but we have detected signs of clouds on exoplanets dozens, even hundreds of light years from Earth. We do not see them directly, but we study the way starlight passes through a planet's atmosphere. As light filters through the edge of an alien world, some wavelengths are absorbed while others pass through. This delicate fingerprint tells us about the gases and particles suspended in the air. In several cases, the data suggests the presence of clouds. But these are not the white, cottony clouds we know. They may be dark, metallic, or mineral-based, formed from silicate, iron, or exotic chemicals. These clouds might reflect starlight or block it entirely, shaping the planet's temperature and appearance. Some planets are permanently shrouded in thick layers, while others show changing patterns across their skies. We cannot see the storms themselves, but we can read the weather written in tea. Some exoplanets orbit closer to their stars than Mercury does. Mercury is already a scorching world, the closest planet to our Sun, bathed in intense light and stripped of its atmosphere. But some exoplanets orbit much closer to their stars, at distances where no planet in our solar system could survive. These worlds complete their entire orbits in mere hours or days. Their surfaces may be molten, oceans of lava churning under a sun that fills the sky. Their atmospheres are whipped away by stellar winds. Some are tidally locked, with one side blistering in unending daylight and the other frozen in eternal darkness. Others are so close that they bulge from tidal forces, stretched like teardrops by their star's gravity. These extreme planets challenge our ideas of habitability, yet they are among the easiest to detect because they circle their stars so often. They are hot, fast, and often unstable, showing us just how flexible and extreme planetary systems can be. Others drift far beyond the reach of any sunlight. Not all planets huddle close to their stars. Some orbit so far away that sunlight becomes nothing more than a faint and feeble glow. These distant worlds may take hundreds or even thousands of years to complete a single orbit. Temperatures there plummet to levels we can barely comprehend. Seasons span generations, and in the deepest cold, chemical reactions may slow to a crawl. Yet even here, planets persist silent and slow, circling their stars at the very edges of gravity's reach. Some may be icy giants wrapped in frozen clouds of methane or ammonia. Others could be rocky and barren, crusted over with ice and carbon dust. Some might even have hidden warmth beneath the surface, sustained by radioactive decay or ancient heat trapped from their formation. These far-flung orbits are hard to detect, but their existence reminds us that planets can survive in places we once thought empty. Even in the loneliest reaches of space, a world can quietly endure. There are planets with spectacular hypothetical ring systems. Saturn's rings are beautiful, delicate bands of ice and dust suspended around a gas giant. But they may not be the most impressive rings in the universe. Some exoplanets appear to have rings that are thousands of times larger, stretching across vast distances, wide enough to eclipse their host stars. One candidate is J1407b, a giant planet or brown dwarf that may be surrounded by a ring system over 200 times larger than Saturn's. These rings could be made of ice, rock, or dust, possibly the remnants of forming moons. As the planet orbits, its rings may cast deep, long-lasting shadows on the star, creating strange dips in the light that we can detect from Earth. If such a planet were placed in our solar system, its rings would stretch across our night sky, visible and vast. They are hypothetical for now, but their shadowy presence hints at the grandeur still waiting to be confirmed. We have only just begun to scratch the surface. For all we have learned about exoplanets, we are still at the very beginning of this journey. The first confirmed discovery was made in 1992. In cosmic terms, that is barely a heartbeat ago. Since then, technology has leapt forward. Thousands of planets have been found, and thousands more await confirmation. We have detected atmospheres, measured sizes and orbits, and mapped their skies in light and shadow. But we have barely begun to understand what these worlds are truly like. We cannot yet see their surfaces. We don't know what they smell like, sound like, or feel like underfoot. We can't say which ones have clouds, continents, or creatures. The truth is, every new exoplanet we discover is a doorway to something we have never seen. As our tools grow sharper, the picture will only grow stranger, richer, and more full of wonder. The cosmos is full of worlds, and we have only just knocked on the door. Some planets orbit so close they are slowly being vaporized. For some exoplanets, being close to a star is more than just hot. It is destructive. These planets orbit so near their suns that the intense radiation and stellar winds begin to strip them apart. The outer layers of their atmospheres heat up, expand, and gradually evaporate into space. Some form long, glowing tails of gas that stretch behind them like comets caught in eternal retreat. Over time, these worlds lose mass, slowly shrinking, thinning, or transforming entirely. One planet, KIC 125575548b, may be crumbling under this kind of erosion, its surface shedding dust and debris with each orbit. It is like watching a planet dissolve in slow motion. These aren't just places to live. They are dynamic systems constantly reshaped by their environment. Even something as vast as a planet can be worn away, little by little, by the unrelenting light of a star. We have discovered worlds that defy all expectations. Every time we think we understand planets, the universe hands us something we cannot explain. We found planets where the skies shimmer with vaporized metal. We found rocky worlds hotter than lava and giant gas planets colder than deep space. We have seen worlds with tilted orbits, backward spins, and rings so large they could block out a star. Some planets are too dense, packed tight with iron. Others are too fluffy, lighter than they should be. Some shouldn't exist at all, at least not according to our current models. But they do. Each strange discovery forces us to rethink how planets form, how they evolve, and what might be possible. Science thrives on these surprises. In the chaos of the cosmos, order is only part of the story. The rest is made of exceptions, edge cases, and quiet contradictions. Little cosmic puzzles scattered through space, waiting for someone to notice them and wonder. Some exoplanets might be water worlds with no land at all. Imagine a planet with no continents, no islands, no shorelines, just endless oceans stretching in every direction. These are water worlds, exoplanets where the surface may be completely covered by liquid water. Not shallow seas like Earth's, but oceans hundreds or even thousands of miles deep. Beneath the surface, the pressure would be intense, enough to compress water into exotic ices and crush rock into unfamiliar forms. Some of these worlds might have atmospheres rich in steam or clouds of vapor circling overhead. Others could be wrapped in hazy mists, warmed by sunlight or internal heat. If life exists on these planets, it would evolve in a deep, sunless sea shaped by currents and chemistry rather than light. We haven't confirmed one yet, but the evidence is growing. If Earth is one kind of habitable world, then perhaps these dark oceans are another kind entirely. We found mini-Neptunes, small but swollen with gas. Not every planet falls neatly into the categories we know. Between Earth and Neptune lies a curious group of worlds called mini-Neptunes. They are bigger than Earth but smaller than our ice giants, and many are wrapped in thick layers of gas. These planets likely have rocky or icy cores surrounded by envelopes of hydrogen, helium, and other gases. They may look similar to Neptune from a distance, but inside they could be wildly different. Some may have deep boiling oceans beneath their clouds. Others might have no solid surface at all. They are too small to be true gas giants, but too big to be rocky super-Earths. For a long time, we didn't even know if planets like this could exist. Now we know they are common, possibly the most common type of planet in the galaxy. Strange, swollen, and still mysterious, they fill in the space between what we expected. Some planets are puffed up like balloons. Some exoplanets are so inflated they seem lighter than they should be. These puffy planets are large in size but low in density. Huge, soft worlds that could float in water if they were somehow dropped into a bathtub the size of a star. One example is WASP 17b, a gas giant twice the size of Jupiter but with only a fraction of its mass. These planets likely formed far from their stars, then migrated inward. Now, intense heat from the star causes their atmospheres to swell and expand. Radiation from the star may be breaking apart molecules, adding to the planet's strange properties. Some puffy planets have visible tails of escaping gas. Others seem impossibly light for their size. We still don't fully understand them, but they show how elastic a planet can be. Not rigid and fixed, but soft, unstable, and stretched by light. There are exoplanets with days longer than their years. On Earth, 1 day and 1 year are very different things. We spin on our axis once every 24 hours, but it takes 365 days to orbit the Sun. Not so for some exoplanets. In certain cases, especially for planets orbiting very close to their stars, The time it takes to rotate is longer than the time it takes to complete an orbit. That means the planet completes a full loop around its star before it even finishes turning once. These planets are usually tidally locked, with one side permanently facing their sun. The night side remains in darkness, frozen and still, while the day side burns under endless daylight. There is no sunrise or sunset, just one eternal face to the light. On such a world, the idea of time itself begins to blur. A day that never ends, a year that races by, and a sky divided forever in two. Some worlds may be covered in thick, hazy skies. We often imagine alien worlds with clear skies and stunning views of the stars, but some exoplanets might be wrapped in thick layers of haze, blocking the light and obscuring everything below. These hazes can be made of complex hydrocarbons, photochemical smog, or exotic clouds of unfamiliar chemistry. On Earth, we see a hint of this effect in places like Saturn's moon Titan, where a golden fog hides the surface from view. On exoplanets, especially those orbiting cooler stars, ultraviolet light can trigger strange reactions in the upper atmosphere, building up thick, murky layers that trap heat and scatter light. These planets may look dull or muted from space, their colors softened by the haze. But beneath the clouds, oceans might churn, winds might scream, and alien landscapes may wait in silence. We cannot see them clearly, not yet, but we know the haze is there, a veil drawn over distant, hidden worlds. We have seen evidence of winds whipping at thousands of miles per hour. Weather doesn't just happen on Earth. On many exoplanets, especially large gas giants, atmospheric winds can reach extraordinary speeds far beyond anything seen in our solar system. Some exoplanets are tidally locked, with one side always facing their star. That intense, permanent heat creates powerful thermal gradients that drive fierce winds around the planet's atmosphere. Using space telescopes, astronomers have detected signs of winds blowing at up to 5,000 miles per hour. That is fast enough to travel the width of the United States in under an hour. These winds can shift clouds, reshape heat patterns, and carry vaporized metals across the planet. Some even redistribute light itself, shifting the brightest part of the planet away from where the star's light hits directly. It is invisible to the eye, but written into the glow of the planet's light, a whisper of motion in a faraway sky. Some planets could be tidally heated from the inside. Not all heat comes from a star. Some exoplanets, especially those in eccentric orbits, may be heated from the inside out thanks to tidal forces. As they move through varying gravitational pulls, their interiors stretch and flex, creating friction and warmth deep below the surface. This is how Jupiter's moon Io stays volcanic. And it happens on exoplanets too. Planets orbiting close to large stars, or caught in gravitational dances with neighboring planets, can experience this kind of tidal heating. In some cases, it could melt rock into magma or keep subsurface oceans liquid beneath thick shells of ice. These planets might look cold or dark on the outside, but inside they are alive with motion. Heat without sunlight, activity without a star. It is a reminder that energy can come from within, and that even in the outer reaches of a system, a planet may still be warm. We have discovered planets in ancient star systems. Some stars are nearly as old as the universe itself, formed in the galaxy's earliest chapters. And around a few of these ancient stars, we have found planets. They have been orbiting for billions of years, far longer than Earth has existed. One example is Kepler 444, a star system over 11 billion years old, with 5 small rocky planets. These worlds are from a time when the universe had fewer heavy elements, suggesting they may have formed from different materials than Earth. What might such planets be like? Could they be worn smooth by eons of impacts? Could they have once supported life long before life began here? We may never know. But these ancient systems remind us how long planets can last, surviving stellar storms, galactic tides, and the slow march of time. They are cosmic elders quietly circling in the deep past. Still here, still turning. Some exoplanets may have moons we have yet to find. Where there are planets, there may also be moons. And yet, for all the exoplanets we have discovered, exomoons, moons orbiting planets outside our solar system, remain elusive. They are hard to detect, small, subtle, and often hidden in the noise. But we have seen hints. Tiny variations in a planet's transit, wobbles in timing, or dips in brightness that don't quite match the model. One candidate, a possible moon orbiting the gas giant Kepler 1625b, is still under study. If confirmed, it would be huge, larger than any moon in our solar system. But even smaller exomoons could be important. They might stabilize planetary climates, shape tides, or even provide sheltered environments for life. Some moons could have subsurface oceans like Europa or Enceladus, while others might be rocky and cratered, drifting in twilight above gas giants. We haven't seen them clearly yet, but they are likely out there, circling in the quiet, waiting to be found. Others could have entire moon systems of their own. Just as planets orbit stars, moons orbit planets. And for massive exoplanets, especially gas giants, it is likely they have entire systems of moons. In our solar system, Jupiter and Saturn each have over 80 moons, ranging from tiny captured asteroids to massive worlds with subsurface oceans. Now, imagine a gas giant many times more massive than Jupiter orbiting a distant star. Could have dozens, perhaps hundreds of moons, a miniature solar system all its own. Some moons might be rocky and cratered. Others could have icy shells or thick atmospheres. A few might even orbit in the habitable zone of their parent planet, shielded from stellar radiation and warmed by tidal forces. We haven't confirmed any of these exomoon systems yet, but the potential is staggering. Not just planets, but whole families of worlds drifting together, locked in gravitational harmony, far from home. Some exoplanets might support life, but not as we know it. When we imagine alien life, we often picture Earth-like conditions. Blue skies, liquid water, and a comfortable temperature range. But life might not need any of those things. Some exoplanets could host life in environments wildly different from our own. In acidic clouds, beneath ice-covered oceans, or in high-pressure atmospheres thick with methane. Even life that doesn't rely on water or carbon or DNA. Extremophiles on Earth already live in boiling acid pools, radioactive caves, and near volcanic vents with no sunlight. So on distant planets, it is possible that life could take stranger forms. Not walking, talking creatures, but microbial networks, chemical colonies, or self-replicating systems that thrive in environments we would find deadly. We may never meet them, but if we listen closely in the light and shadow of alien worlds, we might someday find the first faint signature, a chemical imbalance, a breath of something living. We found planets that barely skim the edge of being stars. There is a line between planet and star, and some exoplanets sit right at the edge. These are giant objects called brown dwarfs or superjupiters. They are massive enough to fuse a little deuterium in their cores, but not enough to sustain the fusion reactions that power real stars. They glow faintly with leftover heat from their formation, and some may even emit infrared radiation. One such object, called HD 100546b, is so large and hot it may straddle the boundary between planet and failed star. We are still debating where the cutoff lies. How massive can a planet be before it becomes something else entirely? These in-between worlds may form like planets or like stars. We don't always know which, but they remind us that categories in space are often blurry. The cosmos is full of edges that shimmer and shift, where one thing slowly becomes another. Some worlds lie right on the edge of the habitable zone. The habitable zone is often called the Goldilocks zone, the range around a star where temperatures are just right for liquid water. But many exoplanets lie right at the edge of this zone where conditions are more uncertain. Too far out and water freezes. Too close in and it boils away. But on the boundary, things become more complex. A thick atmosphere might trap heat, or a high reflectivity might keep a planet cool. And seasonal shifts or orbital eccentricity could cause dramatic climate swings. One hemisphere might be habitable while the other remains too cold or too hot. Life could exist only in pockets beneath the ice, in deep caves, or around volcanic vents. These edge worlds are neither fully comfortable nor completely barren. They are places of tension and potential, where the balance between warmth and cold, light and dark, could tip either way or hold, just barely. And so, we pause our journey here, resting on the edge of these delicate, balanced worlds. We have traveled far tonight, from burning diamonds to silent rings, from winds that scream to moons that wait in the dark. We have seen that the universe is not just vast, it is varied, filled with wonders that challenge our imagination and expand our dreams. But for now, let those images settle. Let the spinning planets slow down in your mind. You are safe. You are still. The galaxy will continue its dance without us for a while. Let your breath deepen. Let the quiet wrap around you like a warm blanket. There are more mysteries to explore, but they can wait. Now is the time for sleep. Good night.